Hey everybody, in this video we're going to continue talking about functions. In the last video we had done these first two objectives, so now we're going to be doing these next two. We're going to use function notation and also find values of a function, and we're going to talk about the domain of a function and find it based on an equation. So let's go ahead and get started. Okay, so function notation. What you want to know basically is that y is f of x, and so normally before you learn function notation you think about plugging in x into an equation and then the output is y. Now we're saying, well, we're going to call that output f, and then specifically of x. And this just gives it a little bit more meaning. It lets us know exactly what we plugged into the function, in this case x, to get a specific y value. Okay, so f of x is the same thing as y. It represents our output. So that's our function notation. And also, this is called the value of the function named f at the input number x. So f is just the name of this function. Sometimes we name them other letters, so you might see like g of x, h of x, and so on. So for example, if we have the function y equals 2x minus 5, function notation would write it like this: f of x equals 2x minus 5. And so that lets me know a little bit more in detail how I get certain outputs. So like for example this one here, this says if I plug in x equals 1, then my output or my y value is -3. Over here, if my x gets plugged in as 3, my output or my y value is 1. So let's just plug in 3 to show you. So if I say f of 3, I'm going to plug that into my function where there used to be an x because it's taking the place of x. So 2 times 3 minus 5. And then that's 6 minus 5, and that's where the 1 came from. So if I plug in 3, I get out 1, and that's my function notation for that example. Okay, so how about this idea here, sort of like a machine? So it's helpful to think of a function as a machine that receives an input number, that's what we call x, and that's from our domain, and it does something to it, like manipulates it, and gives us an output value, or that's in the range, the set of outputs. So normally it will look like an equation, this machine. So for example, our last one, it looked like 2x minus 5 is what the machine did to our input. So we take some number, we plug it in. The last example was a 3. We plug it in into this machine. 2 times 3 minus 5 was 1, and that's what came out of the function. And so the restrictions on the input and the output of the machine are the following. It only accepts numbers from the domain, so we can only plug in numbers that will pretty much produce an output, and those are numbers in the domain. So remember, we learned about domain, but we'll talk about it more today. It's the input, all the inputs, the set that we can plug those numbers into our function. And also for each input, there's exactly one output. It could be repeated, like we plug in one number, we get out a number. We plug in a different number, get out that same number. That's okay. Real quick, let me show you an example so you're not just like, well, what is she talking about? So a random function, let me show you why I'm saying it could be repeated. So let's say our function was x squared. Well, if I plug in 3 into x squared, 3 squared is 9. And then if I plug in -3 and I square it, -3 squared is also 9. Okay, so that's okay. What makes it break, and we talked about this in the last video, is if we had two outputs. So a machine is broken if, let's say, I plug in something like -3 and I get out 9 and -9 at the same time. That would be a broken machine. We wouldn't want that. Okay, so make sure that we only get one output from one input at a time. And then the variable x is called the independent variable, and that's because you can choose x. So x is a choice. So independent means that it's a choice. You can choose whatever x you want to plug in to the machine, into the function, as long as it's in the domain, as long as it's going to produce an output number. And then y is called the dependent variable because it depends on x. So if you chose an x based on that choice, then you're going to get a very specific y value. So your y, in this case, is the dependent variable. It depends on your choice of x. From our last example, when we chose x equaled 3, because of that choice, that independent choice, our only possibility for y was 1. That was the dependent variable from our other example. Okay, and then sometimes you'll see independent variable called argument of the function. So let's take a look at this example. We got lots of parts here to do, a through h. So we have our function. Notice f of x equals 2x squared minus 5x. And we're going to do all of these things. So first, part A says f of 2. So that just means in math language, because math is a language of symbols, this means that when I plug in 2 for x, what is y? Let me write that down, because if you can understand the symbols of math and translate them into words, it's going to help you tremendously in solving these problems. Okay, so here it is. I wrote it in words, and this is one of the reasons why we use symbols in math, because it takes the place of a lot of words. So this right here, f of 2, is exactly the same as this sentence. What does y equal when x is 2? So if it helps you understand what to do, translate it. Translate it into words before you start solving. Okay, so that's what it would be in English instead of math symbols. So where there's an x, we're going to put a 2, and then we're going to simplify and solve. And always put parentheses when you're plugging in, because it really makes a big difference, especially when there's negatives that you're plugging in for your number. So remember your order of operations. First is exponents, so we have to square 2 first. That's where 4 came from. Next is multiplication, so we're going to multiply 5 times 2, and then we're going to multiply also back here 2 times 4. So 5 times 2 is the 10, 2 times 4 is this 8, and then final answer, negative 2. So f of 2 is negative 2. Or another way to say it, y is negative 2 when x was 2. Okay, and we learned about this term last time, but you could say the image of 2, the x number, is this y number of negative 2. But pretty much you want to understand that when you plug in 2 into your function, the output is negative 2. Okay, let's do part B. Notice this one has f of x plus f of 2. Now, notice what we have here. I'm going to actually try to color code it so it makes more sense. Let's go green on this one. Okay, so here's f of 2. So f of 2, we did the work already. It was negative 2 from the previous slide. Okay. The function itself, f of x, was given. We were told this is f of x. And so we're just substituting, and we're keeping this plus sign in the middle because we were told to add the two things. So we were given f of x, so we just write it back, we write it down, and then we figured out what f of 2 was from the previous example, and then we combine anything we can. There's really nothing to combine here. None of these are called like terms. So this is the final answer. If anything combined, like maybe this was negative 2x, we could put that together with them in negative 5x. But on this one, it's already as simplified as it can be. So that one's done. So part C, multiply the equation for f by 2. So that would look like 2 times f of x. Okay, so that's our math symbols, our math notation for it. And we just multiply it by 2. So here was f of x, here it is right here, and we say, well, I want that times 2, times that by 2, and then we will distribute, because that's how this multiplication would work, since there's 2 terms in the parentheses. So that's where we get 4x squared minus 10x, and that one does not simplify any further. Okay, part D, we want negative x in the place of x. So that one looked like f of negative x was the question for part D. That was like, what is this asking? So everywhere there's an x, we're going to replace it with a negative x, and remembering to put parentheses. So recall the original was f of x equaled 2x squared minus 5x, and exactly in the place of x. And if you can understand this and get this down pretty good, then you'll be fine for these problems. Exactly where there was x, you're going to put parentheses in that spot, and you're going to erase it and fill it in with whatever's in being told to you to put in the parentheses. So I'm going to erase that x right there, and then whatever is right here in this parenthesis, okay, whatever is right here, it could be anything, whatever is right here, it could be heart, is going to go right in those parentheses. Okay, that's how you evaluate your function. And so this time it's negative x, and so if we simplify, negative x times negative x is positive x squared. So let me put that off to the side so it makes sense. I'm saying it out loud, but negative x times negative x is positive, because two negatives make a positive, and it's x times x, so it's x squared. So that's this part right here. And then negative 5 times negative x is positive 5 times x. So that is our answer. All right, part E. Notice the negative is on the outside now. So what you can do is think of this as an invisible negative 1. Okay, if you ever see just a negative, go ahead and, if it helps you, put an invisible 1, like write it down, because it's really there. So negative 1 times f of x. So you're going to distribute a negative 1 times this function. So negative 1 times 2 is negative 2, and then there's still an x squared. And then negative 1 times negative 5x is positive 5x. And that is this one. And then part F, we want, the question was, f of 2x. What is f of 2x? So exactly in the function where there used to be an x, we write a 2x. So real quick, one more time, let me show you how this goes. You always go back to your original function and you say, okay, right where there's an x. Okay, I'm just doing it one more time so you really clearly get this idea. Right where there's an x, I'm going to put parentheses, and then I'm going to erase what's there, and I'm going to fill it in with whatever's in my parentheses. In this case, it was a 2x. So I'll just pick a random, another example just to show you. Let's say this time it was smiley face. So exactly where there used to be an x, I put parentheses, I erase the x, and I put a smiley face. And so that's how we simplify and solve these for these function values. Okay, so remember your order of operations. We're going to do exponents first. So 2 times 2 is 4. X times x is x squared. Okay, so that's this part. Then negative 5 times 2x is negative 10x. That's this part here. And then right here, multiply. 2 times 4 is 8, keeping your 8x squared. Okay, so 8x squared minus 10x. Final answer. Okay, almost there. Substitute this time x plus 2, where there used to be an x. So this one was because part G asked for f of x plus 2. So same idea. I won't rewrite it again, but it's exactly where there used to be an x. This used to be x. Replace it with x plus 2. So we erased what used to be x and filled it in after adding parentheses, x plus 2. Okay. So if you think you can simplify this, go ahead and pause the video and try it before I show you what happens. Remember your order of operations, so you're going to multiply this one out with the exponent. So I'll give you a hint on that. You're going to FOIL. So if you remember how foiling goes, or using your box, if you've learned the box method, you have to multiply x plus 2 times itself, because it's a binomial squared. It's something plus something else squared. It could be something minus something else, two terms being subtracted. But either way, you have to work this out by either foiling or using the box method. Okay, so here's what you get when you do that. And then after you foiled that out, you have to then distribute the 2. So then let me show you the final answer, and I'll kind of backtrack and show you some of the steps. Okay, so this is the final answer. This one did have some like terms for us to combine. Okay, so if you forgot how to FOIL or use the box method, you do first times first. So that's where this x squared came from. Then you do outer times outer, 2 times x, and inner times inner, another 2 times x. That's where 4x came from. And then last times last is the 2 times 2. That's where this 4 came from. Okay, and let me just change colors because there's a lot of red going on this screen. So let's just pick green. Over here, negative 5 times x and negative 5 times 2. That's where these terms came from. And then distributing this 2 back here, that's why it's going to be 2x squared plus 8x plus 8. Okay, and then notice that you have some like terms. Let's change the color one more time. We have 8x's minus 5x's. That's where 3x came from. And then we have 8 and minus 10. That's where negative 2 came from. So combine your like terms. All right, so real quick, I want to mention this just because it did come up in this example. If foiling is hard for you or you don't remember it, there's always this other option. So I'll just say or. You can use the box method. If you've never seen this, I really like to show this to people because it's a visual one, and I find that it's actually pretty nice, especially when I'm working with things larger than binomials, like bigger than 2 terms. So x plus 2 is one of my factors. X plus 2 is the other factor. I'm doing this right here. Okay, I'm doing this without foiling. I'm using the box. And then you just multiply every column and row. So x times x is x squared. X times positive 2 is positive 2x. X times positive 2 is another positive 2x. And then 2 times 2 is positive 4. And then notice that these combine to give you 4x. So that's exactly the same answer as this one here. Just another way to do it. Okay, if you like the box method better. All right, almost there. We have part H, I think was our last part. So this time we are wanting f of x plus h. And why x plus h? It might seem random to you, but it's really because this heads into something called the difference quotient, which we will be learning in the next video. So it's really, really similar to the last one we just did. Feel free to pause it and work this out before I show you the answer in case you want to see if you get it right. So pretty much the same thing. You're going to FOIL this part out and then distribute in the back. The difference is just that you have a h instead of a 2 from the last one. Okay, so then after FOILing, you have x squared plus 2xh plus h squared. And then distributing the 5, the negative 5, we get negative 5x minus 5h. And then distribute this 2 from the front to all of those 3 terms. And then, and this one, no terms actually combine, so that would be the answer. Now, we did multiple examples to show that this is going to be the case. When we plug in x plus 2 together like this, it wasn't the same answer. It was not equal to doing these separately, f of x plus f of 2. Similarly, the next one, when we plugged in negative x, it was not the same answer as putting a negative on the outside of our function and multiplying like that. And then again, similarly, 2 times our function was not the same as saying 2 times x and plugging that into our function. And so I want you to notice that these rules that you might think like, oh, I can just split this up. F of 1 plus x is the same as f of 1 plus f of x. No, not the case. Okay, so we're showing these are not true. Okay, so that's why we work these out. Okay, so next let's talk about the different forms of a function. We have what's called an implicit function. The next one's going to be explicit. So basically, if you have an equation and if you see x and y kind of like mixed together, then you'll say that the function is given implicitly. I'll show you what I mean by that in just a minute. If you have y solved for, so if y equals something in terms of x, then it's explicitly given, the function. And so here's some examples. This right here is implicit form. Notice x and y are kind of mixed together, and then this equals 4. But then the same function explicitly written is if we solve this same equation for y. So if you subtract 2x from both sides, you have y equals negative 2x plus 4, or in function notation, f of x equals negative 2x plus 4. And so same thing for all 3 of these examples. The left column over here, these are implicitly defined, it's more so implied what the function is in terms of x and y, and over here it's explicitly stated what y equals in terms of x. So just different names for the types of form of the equation or function. Okay, so now let's talk a little bit more about the domain. So often a domain of a function isn't explicitly stated or specified. So pretty much what you have is the equation, and then you have to figure out what the domain is. And so by definition, the domain of your function is the largest set, so it's just a set, kind of like a collection of real numbers, for which the value of f of x, which is y, is a real number. Okay, so in other words, it's all of the x's that when you plug them in, you get a real number y out of your function. So all of the x's that give you a real y. All right, so the domain of the function is the same as the domain of the variable of x in this expression, f of x. And so let's do this example. Hopefully it'll make more sense about finding the domain. Okay, so question, find the domain. So again, what that means is find all the x's for which when you plug them in, you get out a real number, a real y value. So looking at this function, f of x equals x squared plus 1, what x's can I plug in that when I do that, I get out real answers, real number answers? And so there's actually infinitely many answers or x's I can plug in here. Okay, so the set of all real numbers is the domain for this problem, because no matter what number I plug in for x, no matter what number goes right here, any number I can think of, it just says that I'm going to square that number and I'm going to add 1. Any real number that I square and then add 1 to is still a real number. So that's why the domain is all real numbers. In this case, there's no restriction. I can plug in any number I want into this function and I'm going to get a real number out of it. And so you can write it in words. You could say the set of all real numbers. You can write it like this. You can say any number from negative infinity to infinity. Okay, this is like a starting point. You start at negative infinity, and this is like a stopping point. You stop at infinity, but it's infinite, so technically you don't start and stop. You can also write it like this. You can say this thing here is like script R. It means all real numbers. Or like I said, you can just write it out. The domain is all real numbers. How about this one here? Okay, so you want to think about, is there any x's that when I plug them in, I don't get a real number answer? And this one has something we have to restrict. Okay, so what happens here is if the denominator is 0, that's a problem, okay? Because anything with the denominator of 0 is undefined, right? We've hopefully talked about this before. If you didn't know this, then let me just make this clear. Anytime you have 0 in the denominator, this is considered undefined. So what you want to do is you want to say, well, I don't want this denominator, I don't want it to be 0. So I have to find the numbers that I plug in for x that make this 0. And so I can do that off to the side. And you can solve it a couple of ways. You could say, I'll do it right down here. I can say x squared minus 25 equals 0, and I don't want this to be the case, so technically I'm going to cross this out. But I can solve it by saying either x squared equals 25, or you can factor if you recognize that this factors as the difference of squares. So x minus 5x plus 5. Either way, you're going to get the same answer, negative 5 and 5. So on the left one, if you take the square root, you're going to get x equals plus and minus square root 25, which is 5 with the plus and minus. On the right, you're going to set each factor equal to 0. So x minus 5 equals 0, and x plus 5 equals 0. Okay, and so what you want to recognize is that x, because we didn't want this to be the case, it can't be 5 or negative 5. Because if we plug them in, the denominator is 0, and so the domain is every number but negative 5 and 5. Okay, so let me erase what I have there so you can see clearly one way to write this domain. Okay, so I said it in words, but this is it in set builder notation. So the domain of this function is all of the x's such that, so this little line right here, in math this actually means the words such that x can't be -5 and x can't be 5. So this is set builder notation. If you wanted to do this in interval notation, like kind of like I just did with the infinities, you would say anywhere from -infinity until -5, but I have to like jump over -5. So then I say on the other side of -5, I can pick any number between -5 and +5, and then jump over 5 and any number up until infinity. And then we put this union symbol in between. Okay, this is another way to write the same thing. If it makes more sense, if you've never seen interval notation, think of the number line. If you draw a number line, -infinity would be on the left, infinity would be on the right. And let me just put -5, and let me put 5, and let me put some more numbers so you get reference. 0 would be here, -1 would be here, 1 is here, -6. Okay, just to give you some context. Okay, so I'm just showing you why I just wrote what I wrote in interval notation. So I'm saying any number from -infinity until -5 I can choose. Any number between -5 and 5 I can choose for x. And then any number 5 to infinity I can choose. So that's exactly the same as what we just wrote right there. Okay, that's how we write our answer in interval notation. So interval notation. That other one, I said it, but let me write it. This one is called a set, or set builder notation. Set builder notation, just abbreviate that. Okay, how about this one? So this one is a square root problem. So if you know things about square roots, hopefully it sounds familiar that you might get an imaginary number, and so we would want to make sure we get real number answers. Okay, so this function says that I'm going to take the square root of 5 minus 5t. We only want non-negative numbers inside of our square root. The inside of the square root is called the radicand, by the way. And so we have to restrict that radicand and make it more than 0 or 0. 0 is okay because square root of 0 is real. It's just 0. Square root of anything positive is also real. The problem that we're trying to avoid is square root of anything negative is imaginary. Okay, so we're trying to avoid that. So we avoid it by saying that we want to only take the square root of something 0 or more. Now if we solve this inequality, notice what we get. Any t less than or equal to 1 will work. So quick reminder on inequalities, if you ever divide or multiply by something negative with inequalities, the symbol flips. The inequality symbol flips. So notice right here, this symbol flipped. It's because we divided by -5. Okay, so t is like x in this problem. T is our variable. So as long as we pick a t less than or equal to 1, then this is going to be a real answer. Let me show you what I mean. So let's just say we pick t to be -1, okay? So I have to pick a number less than or equal to 1. So if I say t is -1, watch what happens. H of -1, and then I'm going to plug that into my function. That's a -1. Square root 5 minus 5 times -1. And this is going to give me a real number answer. So this is going to be square root of 5 plus 5, right? Because negative times a negative is positive, which is square root of 10, which is 3 point something. You can use a calculator if you want, but it's real. This is a real number. So this is a real number, which is what we want. We only want to plug in numbers for t, in this case, into our function that'll give us real answers. Watch what happens if we plug in something that is not fitting what we just figured out. Something, in this case, bigger than 1. So how about we pick 2? Look what happens. So h of 2 equals square root 5 minus 5 times 2. That's going to be square root of 5 minus 10. That's a 2, it looks weird. Okay, and that's square root of -5, and right away this is imaginary because square roots of negative numbers are imaginary. Okay, so this is not a real number, and we want real numbers. So we can only plug in t numbers that give us real number answers. And so the domain in set builder notation is right here. I kind of wrote on top of it, but it's right here. All t's such that t is less than or equal to 1. Or this is interval notation. If you think of the number line, let me just put some numbers on there really quick. Negative infinity to infinity. Let's put 1 right here. We'll put 0 and 2. Our answer that we figured out was that the t had to be less than or equal to 1 to work, to give us real answers. And so we can pick anything from negative infinity all the way until 1. And then we can actually pick 1 as well. So I'm going to color in my dot here because 1 is okay because of this equal sign right here. So that's why I have this interval notation. Anything from negative infinity until 1. And then we use this bracket to let us know that we can in fact include that endpoint, the 1. Okay, so if you didn't know this, let me just tell you really quick. You might have already known this, but you use brackets if you can equal the endpoint, and you use parentheses if you cannot equal the endpoint. So it was because of right here, we have less than or equal to 1. That's why we used a bracket on the 1. All right, let's try this one. Okay, so think about it before I talk about it. We are trying to find the domain. You are trying to find all the x's that when you plug them in, you're going to get a real answer. You want this to equal something real, a real number. And so there's two things that we just saw in the previous examples that cause problems. One thing that's not real is when we have an answer that's undefined. That's not a real number. Undefined is like a statement. It's not a real number. So undefined. The other thing that's not a real number is an imaginary number. Okay, so an imaginary number. These are both problems we want to avoid. So I guess we can ask the question, is it undefined or imaginary? If so, we can't use those x's that would make that happen. Okay, and so in this case, we have to talk about two different things. We have a square root on top, and square roots could be imaginary if this is negative. So square root of something negative is imaginary. And then on bottom, we can't divide by 0. So if this is equal to 0, this is undefined. So we have to consider two problems, and we have to avoid them because we want this to be a real number. So let me kind of get rid of this part, because now what we're focusing on, we know what we want. We want this to be a real number. We're focusing on what would cause a problem. Okay, so in this case, we have to do two separate things. We have to say, well, when is this square root going to not be negative? So you set 2x right here plus 6 greater than or equal to 0. And if you solve this, you subtract 6 and divide by 2. That's where this comes from. X is greater than or equal to -3. So just from saying I cannot take the square root of anything negative, so I set it greater than or equal to 0. That's this part. Okay, so this is addressing the imaginary part right here. And then separately, I can't have the bottom of my fraction be 0, because then it's undefined. So I have to say, well, this denominator cannot be 0. So x minus 2 can't be 0. So if I add 2 to both sides, x can't be 2. So I have to keep both of those things in mind, and putting those together tells me what I can choose, the domain. So the domain is all of the x's such that x is greater than or equal to -3 as long as it's not 2. Okay, so let me show you on the number line, because I think that might help you make more sense of it, especially if you're a visual person. So what numbers for x can I pick? Because the domain questions, when the question is, what is the domain? So that's the whole question, remember? you're trying to find the x's that work. So I want to make that clear what we're doing. Find x's that produce or give us or output. So we'll say produce real numbers. Okay, so we figured out x has to be greater than or equal to -3. We also figured out x can't be 2. So let me just put those numbers on the number line and show you how to put those together. Okay, so 2 is here. All right, so thinking about what we found out. X has to be greater than -3. So anything greater than -3 is fine. But we were also recognizing x can't be 2. So I can't pick 2. I have to exclude that. So I'm going to go ahead and erase this because, oh, no. I have to like jump over 2. Okay, so from -3, I have to jump over 2. I can't pick it. But as long as it's -3 or more, and I can pick -3, so I'm going to color that one in. Okay, because there's an equal bar on it. So my answer in interval notation would be from -3 with a bracket, because I can equal -3. I can go all the way until 2. I can pick -1, 0, 1, and 1.9. I just can't pick 2. But then I can pick anything bigger than 2. So I can pick 2.1, 2.2, 3, 4, 5, 10, a million, all the way to infinity. So this is the same answer in interval notation. Okay, so this is the domain in set builder notation. This is the same answer, domain in interval notation, which I got from the number line here. So let me hopefully make this very clear. When you are asked to find the domain of an equation or a function, these are the things you want to look for. If it has a denominator, you set the denominator equal to 0, and you figure out what causes that to be a problem, and you get rid of it, you exclude it. If the function has a radical, you're going to take the radicand, you're going to take what's inside the square root. So it's called the radicand, but basically you take whatever's inside the square root right here, and you just say it has to be greater than or equal to 0. And you do those things, and then that's going to give you whatever's left will be your domain. All the x's you're allowed to plug in, because they'll give you real answers. And so the domain of the function can be written, we showed examples, in interval notation, set or set builder notation, and you can actually do it in words. I've been saying it out loud in words, but we've been writing it in interval and set notation. And so we say that f is defined at x, or f of x exists as long as that x number is in the domain. The domain is just the set of all the x's we can plug in. If x isn't in the domain, we say f is not defined at x, or f of x does not exist. For example, let's say real quick, if your function was, let's say 1 over x, the function would not be defined at 0, because 1 over 0 is undefined. And then let me give you another one. Let's say the function is square root of x. Well, the function would not be defined at anything negative, at -1, -2, and so on. It wouldn't exist. It'd be imaginary. All right, so this will be our last example for this video in this part of the section. So express the volume of a cube as a function of its side length, and then find the domain. So find the numbers that you can plug into this volume formula is another way to say that. So the formula for the volume of a cube, and based on its side lengths, is one side times the other side times the last side. So these are all the same size. So it's s times s times s, or s cubed, equals the volume. And then if s is our independent variable, you can choose the side length for your cube. V depends on our choice, so V is a dependent variable. And then if we want to talk about our domain, we can plug in anything greater than 0. Okay, so this is our function notation for the volume of a cube, where our input is side length. And then the domain, anything we can plug in that will give us a real answer, a real volume, is greater than 0 for the side length. Because think about it, if this was like a physical cube, I'm not going to have any, if it's 0 as a side length, then my cube doesn't exist. If it's negative, that doesn't make sense because I wouldn't measure it and say it's negative. So anything more than 0 would be our domain. Okay, so that is it for this one. In the next video, we'll talk about difference quotient. For now, thanks for watching.